On the board there, you've got the diagram of Eratosthenes, okay? Eratosthenes, or however you want to pronounce him. He lived, as you can see, if you look at the towns and so forth, he lived in the north of Egypt, and he lived around a couple hundred years BC, okay? He did a very famous experiment to prove that the Earth is round. So he proved that the Earth is round, and he was one of the first people to give us a reasonable measurement for its size. Okay? So this is a really important experiment, and the details of it are in your specification. All right? If you read the spec, you will find Eratosthenes' experiment is specifically mentioned, which means in the exam they can ask you quite detailed questions about it. All right? So you not only need to know that he did it, you do need to know the details of how he did it. Okay? In the first of the two packs on the history of astronomy, the one about ancient astronomy, a few pages in, you've got this diagram. Okay, I'm sure you can find better ones on the internet nowadays, but it shows you basically the idea of the experiment. Okay, let's have a go at drawing it then. First of all, quick map of Egypt. As I said, long thin country with River Nile down the middle. Somewhere near the mouth of the Nile on the Mediterranean is a very famous town called Alexandria. Okay, Eratosthenes worked in Alexandria. Okay, Eratosthenes worked in Alexandria, and he was apparently librarian of the Great Library of Alexandria. Okay, so he knew a fair bit about what was going on. He had access to, well, they would have been scrolls and things in those days, but he had access to a lot of ancient knowledge and thought and things. Okay, and he read, apparently, the story goes, he read about a town in the south of Egypt, okay, which is called, or it's called in his time, Syene. Okay, if you look at it on a map nowadays, I don't think it's called that anymore. It's called Aswan. It's famous for the dam that they built there in the 20th century. So he read about what goes on in this town, some way south. Okay, and he read, as you can see from the diagram, that on June 21st, on Midsummer's Day, the sun was directly overhead. Now that's the kind of thing people would write about. I mean, it never happens in Skipton, but if you ever go to these sort of southerly latitudes, you can get the situation where in the middle of the day in the summer, the sun doesn't just get very high in the sky. I think in Skipton it's about 60 something, Midsummer's Day. It actually goes completely overhead, which means you have no shadow, all right? If you look down a well, you just see a reflection of the sun, and you can see down the sides of the well, all right? It's quite a spectacular event, and people in Syene wrote about it, and there would have been a good deal of traffic up and down the country, all right? People would have traded up and down Egypt, Upper and Lower Egypt, and so the information about it, the stories about it, would have got back to Eratosthenes in Alexandria, okay? So here's the key information about the experiment that you need. June the 21st, famously the summer solstice. In Syene, if you were to put a stick in the ground at midday, then you would find that the sun was directly overhead and there would be no shadow. Okay? Now, Eratosthenes wasn't just a librarian, he was a scientist, and he thought, well, let's go out and try this out. So he waited for June the 21st, and he went outside in Alexandria, and he did exactly the same experiment. Okay? Put a stick in the ground, waited to midday when the sun reached its highest point, and waited to see what would happen. And he found that there was a shadow. Okay, on June the 21st, a Midsummer's Day in Alexandria, on the coast of the Mediterranean, so further north, there is most definitely a shadow. All right? The length of the shadow, you've done all about sine and cosine in your maths lessons, he used the length of the shadow, the length of the stick, to work out that the sun wasn't overhead, it was at an angle of 7.5 degrees. So in Syene, the sun is directly overhead, and in Aswan, the sun is at an angle of 7.5 degrees. Okay? So it's 82.5 degrees above the horizon. You with me? And this, at first, was a bit puzzling, because if you think about it, that's very strange. It's strange, though, only if you have a flat Earth. If the Earth is flat, and the important thing here is to remember the sun is a very long way away. If you look on the diagram, you've got some ruled lines there that remind you that the sun is a very long way away, which means its light is effectively, by the time it reaches the Earth, parallel. So you have to imagine, like railway tracks, these vertical lines, all parallel, coming out the ceiling, which are the sun's rays. Okay? Now, on a flat Earth, it's easy enough to understand Alexandria and Syene both having no shadow. All right? If you're the sun, then that's perfectly possible. All right? It's perfectly possible, if you're at a bit of an angle, to understand. You with me? It's perfectly possible to understand both places having a 7.5 degree shadow. But how one of them can have no shadow and the other one have a 7.5 degree shadow doesn't make sense unless. Do you see? Think of the vertical lines coming out the ceiling. You can have one place having no shadow, at the same time, somewhere else is having a, roughly where my hand is here would be where the shadow would be. Okay? So that was a really important observation. The observation that this happens and this happens at the same time, Midsummer's Day, 21st of June, you get this. You get no shadow in this place and you get a 7.5 degree shadow in that place. Eratosthenes has basically proved that the Earth is round. All right? You can't have a flat Earth. There was other evidence around at the time. Many people were convinced the Earth was round. Ships going over their horizon, the hull disappears for the mast, etc., etc. But this was perhaps the first real scientific observation, the first experiment that actually proves that the Earth is round. Okay? And notice the date, is it up there? 240? Yeah. Round about 240 BC. So if you've got this idea that everybody before 1492 was stupid and thought the Earth was flat, and Christopher Columbus set off in 1492 and proved the Earth was round, just where would you start with that? That's just complete nonsense. Eratosthenes had proved the size of the Earth, the shape of the Earth, in 240 BC. Now, Eratosthenes went on a bit further than this, and he used this information to work out the size of the Earth. Okay? If you think about it, then if this is the shape of the Earth, it's a curve, which means one place gets no shadow, at the same time another place gets a decent sized shadow. All right? How big a shadow am I going to get at this place depends on, if that's the Earth, how big a shadow I'm going to get at this place depends how far around the Earth it is, doesn't it? All right? So, this 7.5 degrees is really important, because this 7.5 degrees is obviously part of, it shows you how far is Alexandria round the Earth from Syene. All right? The distance from Alexandria to Syene is obviously equivalent to 7.5 degrees. So let's go to the more useful diagram now, which is the one with the round Earth. What you've got, let's try and do it the same way as the diagram on the computer. Let's put Syene at the top. Doesn't mean Syene's at the North Pole. Right, there's Syene with no shadow. Okay? Alexandria over here, from the same parallel sunlight, badly drawn, gets its 7.5 degree shadow. Okay? What Eratosthenes realised was that distance there must be about the same as 7.5 degrees round the Earth. He said 500 miles, which is approximately the distance between Alexandria and Syene. Okay? He would have known that fairly accurately, actually. Again, he was fortunate to live in this country. Egypt is just perfectly set up for astronomical discoveries, because the country is laid out north-south, so you'll see differences in the stars, and from a very, very ancient time, you've had reasonably efficient communication up and down the country. All right? I think we mentioned in the past, countries like China and many other great ancient civilizations often didn't notice these things because their country is arranged east-west, where of course you see pretty much the same stars. Okay? Egypt is perfectly designed for doing this. The story goes, you read a lot of books, they say got a man to pace out the journey. I don't think that's true. What's probably more likely is up and down Egypt at the time there would have been people sailing boats, there would have been people with camels and things, and if you went into the market at Alexandria and said to a camel trader or a boatman how long to Syene, they could tell you. They could tell you exactly how long it would take to get to Syene. And they knew roughly how quickly they were going. So I think that's more likely to be the case. Even in ancient times, even in 240 BC, he would have been able to get a pretty accurate measurement for the distance between Alexandria and Syene. And it's simplified by the fact they're basically just perfectly north-south of each other. Okay? So he would have had a fairly accurate estimate there of about 500 miles. Okay? And he basically said the further round Alexandria is, then the bigger the shadow difference would be. If Alexandria were here, you'd have a 90-degree shadow, which would be quite impressive if you think about it. But anyway, he said basically this is the plan. 7.5 degrees must be equivalent to 500 miles. If you're thinking, what have I got to get straight in my head for the exam, it's this. The 7.5 degree difference, 0 degrees shadow here, 7.5 degrees here, must be equivalent to 500 miles. So he said, well, 7.5 degrees, how many times does that go into 360? It's about 50, isn't it? Can you see? You can check the numbers a bit more carefully on the sheet, but he said basically 7.5 degrees is about, I think it's a 48th actually, isn't it? It's about a 50th. 7.5 degrees is about a 50th of a circle. And so this is the key sentence. Alexandria to Syene must represent a 50th of the Earth's circumference. All right? That's the key thing that Eratosthenes spotted, is the 7.5 degrees between Alexandria and Syene means that this distance here, this 500 miles, approximately, this 500 miles must represent about a 50th of the Earth's circumference. So how are we going to get the Earth's circumference? Times it. Yeah. If 500 miles is a 50th of it, all you've got to do is multiply them, and you get obviously about 25,000 miles. Yeah. Which isn't bad. It's quite close to, you can look it up for homework, it's fairly close to the true value. All right. So Eratosthenes' experiment proved the Earth is round, okay, and also gave us the first really accurate measurement of the size of the Earth. Okay. And as I said, Christopher Columbus, people like that, knew about Eratosthenes. There's a slight problem with this number. Eratosthenes didn't measure in miles. Eratosthenes measured in the Roman unit of decent-sized distances. The stadium. Well done, lads, I'm sure. The stadium, lots of them being a stadia, which is where we get our word stadium from. We're not quite sure. It's one of those things that's got a bit lost in history. Exactly how big? Do we have 2 mileposts exactly 2 stadia apart or something like that? We don't. We don't know exactly how big a stadium was, the unit of measurement that Eratosthenes would have used. We know it can't be bigger than this and it can't be smaller than that. We don't have it exactly. There is quite a bit of leeway. Okay? If you take the smallest estimate for a stadium or the largest one, Eratosthenes can actually be quite a long way out. All right? So we are being a little bit generous to Eratosthenes here. His value may have been out by quite a bit. We don't know exactly because the units he gives us his answer in, the stadium, we don't have an exact measurement for that in miles. Okay? But as I said, very, very important experiment. How we missed it out in the section on history of astronomy, I do not know. But as I say, it is specifically in your specification. All right? So you need to know, how does it work? You don't need to remember the numbers. They'd be given to you if you needed to use them. But you need to know the principle of it, which is this difference in angle must be equivalent to that distance there. That distance there must be a 50th of the circumference of the Earth. Okay?